Alright, let's get started with chapter 16 on the normal distribution. 16a will be an introduction to a specific continuous function, which is in this situation, a probability density function. And we'll look also at how to transform a normal distribution into a standardized form, which is easier to then to not only draw but also do some probability calculation. All right. First, let's start with the standard normal distribution. So it is a bell-shaped curve. This is the actual function, so don't worry too much about the function itself. All the calculations later on will be done on using a CAS calculator, so there's no manual integrations or calculus operation. And notice the domain is R for the function. It's also positive, and because it's a probability function, the whole area here is going to be equal to 1. Also, the mean, which is also the axis of symmetry, is going to be the y-axis, or x equals 0. And as you increment to 1, it will represent a 1 standard deviation for each unit. What did I forget? Oh, the function is even, so the y-axis is the axis of symmetry. Also, as you go towards infinity here on the positive side, negative side, the horizontal axis, which is the equation y equals 0, is an asymptote. And the deviation I mentioned is called the standard deviation. And finally, the variable, the random variable, is annotated capital Z, and that's the notation for the standard normal distribution. Now, the normal distribution, which is the general one, is a transform from a it can be transformed into a standard normal distribution, which is what we've seen before. So the features of a normal distribution is you will know the mean, which is the mu symbol, and it will have its own standard deviation, sigma. So what we do with this variable, if we do those respective mapping of those transformations annotated here, you will get to the standard normal distribution. So the transformations that you have here, you have first a translation of mu units in the negative direction of the x-axis. That will bring back the mu value to 0. Then you will have a dilation factor of 1 over sigma from the y-axis. So here, that's what we have here. What will be is it will be a narrower bell-shaped curve, and then the last is a dilation of factor sigma from the x-axis. What it means is the peak of the bell-shaped curve will be higher by a factor sigma. By doing those two dilations, what we do is you maintain the area under the curve. Remember, the whole area needs to be equal to 1 or 100% because we deal with probability. That will be, so when we apply the transformations to standardize, what you would have is your density function as it is here, which is quite complex. But notice how you have your transformations here, and you have a sigma here for the dilation from the x-axis. Now, the second expression is probably the most important, is when you have a probability and x is less or equal to a certain value a. As we do the transformations, what we do is minus mu and divide by sigma. Then we end up with the standard random variable. So now we have what we call, that process is your standard normalization. You will have some properties. Some of them are already mentioned. So it is a normal distribution. The probability that you try to determine is the area under the curve, and the boundaries will depend on the inequation on the probability. The total area is 1 or 100%. So this is what it's the same for all probability density functions, which is not covered in 2020. It is covered, however, in chapter 15. The graph of the normal density function is symmetric and bell-shaped. The center is determined by the mean of the distribution, which is also your axis of symmetry. The width is determined by the standard deviation. Here, so the example, you have a normal distribution with a mean of 3 and a standard deviation of 2. So this is the bell shape on the right. That's the mean of 3, and the standard deviation 2 is telling us how wide it is. Okay, the transformation to turn it into a standard normal distribution is, you will have a dilation of factor 2 from the y-axis. Hang on, let me see. Hang on, I'm going backwards, so let me rephrase that. Here you have your standard normal distribution. You will dilate from the y-axis by a factor 2, so that will become wider. From the x-axis by a factor half, so the peak is halved, and then you translate 3 units in a positive, so you move into the mu value. Okay, and that's it for 16a. See you later.